Welcome back to the workshop. We want to continue taking a look at section 2.2 on equivalence relations. And we'll finally get to this special instance of equivalence relations, right? We've talked about relations already, so now let's take a look at these particular ones of interest, equivalence relations. So a relation which is reflexive, symmetric, and transitive, so a relation that does satisfy all three of these properties, is called an equivalence relation. Okay, cool. So there's one equivalence relation that everyone is familiar with, and that is equals. We're familiar with it on several different sets: the real numbers, the integers, the rational numbers, complex numbers, even sets, right? We've talked about when two sets are equivalent as well, right? And we would use the equal sign to denote it. So we've seen the idea of equals quite a bit, right? The number 2 is equal to the number 2. Okay. And if the number 2 is equal to the number 2 and 2 is equal to 2, then we get that 2 is equal to 2. Okay, so every number is related to itself. It's symmetric because, right, I can change the order and it doesn't matter. And we have transitivity. Now it all seems very trivial. It seems really silly. And the biggest thing here is that what will happen is that there might be different representations for things. And when there are different representations for things, then it becomes less obvious that two things are or are not related, or that the relation may have these properties. But we won't even necessarily see that particular problem here. We'll look at some equivalence relations that are interesting and are not quite so trivial. So let's see one such example. So let's let S be the set of integers greater than 1. So 2, 3, 4, 5, 6, and so on. Let's define a relation, x is related to y. Let's define it to mean that the largest prime divisor of x equals the largest prime divisor of y. Now that in and of itself, right, that didn't have any order. If the largest prime divisor of x is the largest prime divisor of y, then of course the largest prime divisor of y is the largest prime divisor of x. So we can see some things immediately. In particular, we should immediately see that it's both reflexive and symmetric. But we want to take advantage of this example as a time to demonstrate how to show that the properties are satisfied. So in this case, we want to show that this is an equivalence relation. So I'm telling you it is reflexive, symmetric, and transitive. And we want to show that it is each one of these things. So I'm going to write down each of the properties we want to show. Reflexive. And then we'll show symmetric. And we'll show transitive. All right, so I'm going to end up moving these things around. And to make sure everyone can read what I'm writing, I'm going to go ahead and use the typewriter function here for these. So I want to show that our relation is reflexive. So for any integer x, which is greater than 1, so for any integer x greater than 1, of course, the largest prime divisor is equal to itself. Of course, the largest prime divisor of x is the largest prime divisor of x. So x is related to itself. So x is related to x. And R is reflexive. Right? That's as simple as that is. Cool. Nothing too complicated. All right. What about symmetric? Let's assume, assume that x is related to y. So once I say that x is related to y, I know that x and y are integers greater than 1, and that they have the same largest prime divisor. So let's let p be the largest prime divisor of x. Since the two are related, since x is related to y, p is also the largest prime divisor of y. Excellent, right? Because they're related, we know that p is also the largest prime divisor of y. And this allows us to make explicit the statement that y is related to x. So that is the largest prime divisor of y is equal to the largest prime divisor of x. Excellent. What does that tell us? Well, hence, y is related to x. And once we know that y is related to x, whenever x is related to y, we have that R is symmetric. So again, what I want to do is I want to show that whenever x is related to y, that's what I assumed, whenever x is related to y, I know that y is related to x. When I say that, I'm saying that it's true, right? I'm saying that this thing is true, and I have that it is symmetric. Excellent. Now, what about transitive? Well, in order to show transitive, we need to start with x is related to y and y is related to z. So let's assume that x is related to y and y is related to z. And I want to show that whenever this is true, whenever the x is related to y and y is related to z, I want to show that I could skip over the y and have that x is related to z. So that's what we want to do. We want to show that x is related to z. And it's essentially the same thing as showing symmetric for this example. So again, we're going to let p be the largest, let's see here, the largest prime divisor of x. Once we have that, we can say that y has the same largest prime divisor. So since x is related to y, p is also the largest prime divisor of y. Excellent. So now we know that p is the largest prime divisor of y. But since y is related to z, we get the same result for z. Since y is related to z, p is also the largest prime divisor of z. Fantastic. That is the largest, right? What we want to say now is we want to say the condition that's needed for x to be related to z. So we know that they have the same largest prime divisor. Now I just want to say it. I want to make it explicit that they have the same largest prime divisor. So that is the largest prime divisor of x is equal to the largest prime divisor of z. That statement is what allows us to say that x is related to z. Once I have made that statement, once I've said that the conditions are satisfied for it to be related, then I can say they are related. Okay. Explicit conditions explicitly met. Now, we say that it's related. Hence, X is related to Z, and R is transitive. Excellent. And that's all that we need to show for this example. We wanted to show that it satisfied the three properties. Of course, what's now a good idea to do is to say that since R is, let's see here, same in the same order, reflexive, symmetric, and transitive, it is, in fact, an equivalence relation. Awesome. So we showed that it satisfied the three properties, and then we finished off by saying, hey, I am aware that the definition of equivalence relation is to satisfy these three properties. So now that I've shown that it satisfies the three properties, I'm saying it is an equivalence relation because I've just demonstrated that it satisfies the definition of equivalence relation. It's very important that we do that. Of course, I can see that you might show that a relation satisfies these three properties, but I don't know if you're doing it because I said to do that, and that's the work that I did, or if it's because you understand that those are the conditions required to be an equivalence relation, okay? And by making this statement at the bottom, by making the statement of, hey, it is these properties, or it has these properties, so it is an equivalence relation. That tells us that you understand why you just showed what you did. So we showed this because these are the conditions required for it to be an equivalence relation. Excellent. So that's all I wanted to share in this video. We've got one more video coming with one more definition and example in it. So I'll see you guys back in the workshop very shortly.